we need to first introduce what it means by a user to be a member of a row. So we are given a configuration of the system is given as a pair, and U is a set of all users in the system, and a binary relation UR defines which user are members of which rows. And we would like to point out that the notion row is just a named set of users. Our algebra can be replaced into other user attributes. So our algebra can apply to contexts other than row-based access control. And given a configuration, if the term phi is all, then a set of users satisfy the term if the set X contains exactly one user, and when phi equals to a row, a set of users satisfy the term if the set contains exactly one user who is a member of the row. And when phi equals to a set of users, then X satisfies the term if X contains exactly one user that is also in the set. And when the term phi equals to a negation of another term, then the set X satisfies the term if X contains exactly one user and X does not satisfy the subterm phi 0. And when phi equals to the closure of another term, then X satisfies the term if X is non-emptied and every user in the set X satisfies the subterm phi 0. And when we use a square cup to connect two subterms, then a set of users satisfies such a term if X satisfies either of the subterms. And when we use square cap to connect two subterms, then X satisfies the term if X satisfies both subterms. An interesting case is when we use O times to connect two subterms. Then a set of users satisfies such a term if and only if X can be partitioned into two disjoint sets such that each such subset satisfies a subterm. And when we use O dot to connect two subterms, then X satisfies the term if X contains two subsets and the union of these two subsets equals to X, and each of these subsets satisfies a subterm. The difference between O dot and O time is that in O time we require that X1 and X2 be disjoint, but for O dot, X1 and X2 may intersect. So next, I would like to show you some more sophisticated terms to demonstrate the expressive power of the algebra. So in the first example, such a term means that requires any two users out of a set of three users. And the second term requires that every participants must be either an accountant or a treasurer, but there is no bound on the number of participants. And the third term gives a requirement on the two users participate in the task. So it requires a set of two users. One user must be either a physician or a nurse, and the other users must be a manager but not an accountant. And the last example requires a manager, an accountant, and a treasurer, and every participant must be a clerk, but Alice and Bob cannot participate. After seeing this syntax and the semantics of the algebra, we would like to have a look at the algebraic properties of the algebra. And so all the four binary operators in the algebra are commutative and associative. And as square cup and square cap distribute over each other, while O dot and O time distribute over square cup. And however, no other order pair of binary operators have the distributive property. And the algebra also has other properties that allow us to rewrite a term into another equivalent term. And in particular, the algebra satisfies the De Morgan's law. So let's go back to think about what the term in the algebra actually defines. So given a term can be satisfied by a set of users, and given a certain configuration, there may be like a number of different user sets that can satisfy the same term. So from such point of view, a term defines a set of user sets that satisfy the term under a certain configuration. So let's take a look at an example. And in the configuration, Alice and Carol are members of clerk, Bob is a member of accountant, and Dave is a member of treasurer. And we are given a term phi, which requires a clerk, which requires two users. One user is a clerk, and the other user can be either an accountant or a treasurer. So in this case, the term phi, because in such a configuration, there are four sets of users that satisfy the term phi. So in this case, phi actually defines a set of four sets of users. And next, I would like to talk about the rationale of the design of the algebra. So, from the definition of the semantics, the algebra, the term satisfaction for the algebra is not monotonic. That is to say, if a set of users satisfying a term does not imply that a superset of that user set also satisfy the term. So for example, in such a configuration, the user set Alice and Bob satisfy the term phi. However, a user set Alice, Bob, and Carol does not satisfy the term phi, because phi requires exactly two users. So you may wonder why we design term satisfaction this way. The reason is the current design, which is not monotonic, is more expressive than a monotonic design. For example, if we are given a policy saying that a task requires two accountants,